The technical difficulties are ridiculous right now. I don't even know why. Why? Okay. All right. Okay, what do you girls want to work on?
I needed help on the chapter 26, page 496.
Okay.
I just don't get anything.
To put it bluntly, I don't know what I'm doing. Hi, Miss Kaya.
Hi.
There you are. All right. Okay, so 496. Which question?
Number 3.
Okay. Okay, perfect. Let's start there. Let me see if I can turn this up. Okay. Welcome to my document camera. Ah, brilliant. Okay. So, so page 496. Number 3, why is that so blurry? Hold on. I don't know why it's blurry. It's not usually. Okay, well, that'll have to do for now. Maybe. Okay. All right, so page 496, number 3. One kind of plant has only blue and white flowers. The offspring have a 75% chance of blue. Ah, why can't you read that? I don't know why it won't focus. Guys, I've done this like 7 times and it works always. And now it won't. Will you, Taylor, will you go grab London's phone for me? Tell her I need to borrow it. Sorry, I don't know why my video won't focus. Okay, so let's just talk through it, and then as soon as I have a camera that is working better, I will show you. Okay, so there's a 75% chance that the flowers are going to be blue. And that's just like, according to genetics, so that right there, that number that it's giving you is the expected. they're not saying that they went around to every plant and observed that 75% were blue. They're saying that the way that they designed the genetics, that should be 75%. So that is going to be what is expected. Independently of one another, 200 seeds. So we're going to have 200 seeds. That's going to be our sample right there. And then 142, so of that sample, 142 turned out to be blue. So it's just asking, is the 142 close enough to the expected value that we don't really see any problems with it? Or do we feel like it's super far off? Okay, so really quick, just throwing this out there, what number do you expect? If there's a sample of 200 and 75% are supposed to be blue, how many do you think are supposed to be blue?
150?
Yeah, so we're expecting, our expected value is 150 blues. Okay, and then where, there it is. Sorry, I'm just gonna get this turned on really quick, but I can't remember the password to my own meeting because I didn't know how to make it a cool password. There. There, now you can see it. Okay. All right, so our expected value is gonna be 150. Let's just think for just a second about what's in our box. Yeah, I know we already came up with expected value and usually we do that after the box, but let's just think about what we could put in here. Any ideas?
Could we do like the ones and the zeros in this one?
Yeah, I would, because we're just counting how many are actually blue instead of like finding an average test score or an average speed or something like that. We're just trying to figure out how many are blue. So we're gonna have ones that represent blue flowers, and then we're gonna have zeros that represent white flowers. But how many blues and how many whites?
3 blues and 1 white.
Good. Because why?
75% of them are blue.
Good. 75% blue. Okay, and so out of here, we're going to draw how many times?
200?
Good. Perfect. So obviously with replacement, there's only 4 tickets in the box. We're definitely going to have to be putting them back. Okay, so expected value, does this still make sense even with changing up that box a little bit? So we would just find the average of the box, yeah, which would be 3/4 basically, right? Add them all up, you'd get 3, divide by how many there are, 4. So 3/4 of, so this would be 3/4 times the number of draws, which is where we get that 150 from. Okay, and then we need a standard error. We need a give or take. So we think it's going to be 150 blues, but obviously there's going to be some give or take on that. So let's figure out what that give or take is. Okay, so I don't know what I just did. Okay, So standard error, again, we're just counting, or so we can think of it as we're finding the sum of the draws, or the count. So standard error is going to be just our SD and the square root of the number of draws. And so SD, how do we do SD of a box like this?
Everything's under the square root, and it's the fraction of 1
Good.
times fraction of 0.
Good, so we can do 3/4 and 1/4. We could do 0.75 and 0.25, it doesn't really matter. And then square root of the number of draws.
On the bend.
So square root, oh, wow. Okay. So we expect 150 of those seeds to turn out blue, give or take 6. But what they actually observed is up here. They observed 142 blue. So our job is just to see how far away that is. On number 3, it's not necessarily asking you to go through the full process of writing out a significance test. You are always welcome to go through that full process of writing out the significance test, but it is not, if it doesn't specifically ask for it, it's not required. If I were, just to review all of that part too, if I were to write this out as a significance test, I should have started technically with this and this. So the null hypothesis and the alternative hypothesis, okay? Again, null is no change. So no change from what's expected. Nothing is different than what they are advertising. No change has happened, since data was taken in the past. It's always just no change, nothing new. So this is going to be that 75%. So 75% of the flowers are blue. Okay, and then right here, this is a place where I'm losing a couple of students because we have 2 options right here. Until we get to chapter 29, chapter 29 is the place in your book where they finally come back and say, hey, guess what? You're not actually supposed to perform the experiment before you write your hypothesis about that experiment. You're not supposed to watch what happens and then write down what you think is going to happen. It's just not good. Okay, so it's kind of like cheating, I guess, in a way. So if I am running a hypothesis test about how many of the seeds are going to turn out blue, then I shouldn't look at that 142. I shouldn't look at what happened in the sample before I write my alternative hypothesis. Okay, so we want to read very carefully in number 3, and it says 200 seeds, 142 turn out to be blue flowering. It just says, are the data consistent with the model? Notice in that question, it's not suggesting that the data are too low or too high. It's just asking, is it consistent? Is the data close to what is being advertised? When you aren't given a question where it's leading you one direction or the other, then you technically should do what we call a 2-tail test. So my alternative hypothesis right here shouldn't be that less than 75% or more than 75% are blue. We're just going to say not 75% are blue. Okay, we're just saying it's some other percentage. It could be higher than 75%. It could be lower than 75%. Now, let me just give you an example of the other way around. If they, again, and this is just pretending, closing your eyes and pretending you didn't see the 142. But if in the question they had said run a hypothesis test to see if this particular batch has too many blue flowers. Then you would do that the alternative hypothesis is that it's greater than 75%. Does that make sense? Do you see the difference between those two options? Okay, so just saying that, and that's kind of ugly wording. I maybe could have written that in better language, but I chose not to, obviously. Not 75% are blue. Yeah, that's kind of weird. Anyway, but we're just saying it's just not exactly 75%. It's up or down, one or the other, okay? So then that's when we go through this whole process of creating a box. So technically this should have been step 1. Okay, this right here should have been step 2 to create the box and do all of that stuff. And then step 3 is when I come up with these numbers, our expected value and our standard error. Now we're going to go ahead and standardize the values. So step 4 is when we're going to actually take the observed value and turn it into a z-score. I want to know how many standard errors away that 142 is. So 142 minus 150 and divide that by our standard error. Okay.
Can you just divide it by like, sorry, is it okay if we just divided it by like 6?
Yeah, absolutely. I would just right here, if you're writing this out, I would just say, oh, that's close enough to 6, so I'm going to use 6. Yeah. As long as it's a deliberate decision, I won't call you lazy, I promise. That's a good idea. So I'm going to just do 6. So we're going to do a z-score of negative 1.33. Okay, and then I'm going to look that up. So a z of 1.33, we're going to actually have to use 1.35. So that gives me an area of 82.3. Now, pause for just a moment, because what did we just find? What is this number?
That's like the area of the middle of the...
Good. So if I were to sketch this out, the expected value is 150. I found that 142 was about right here at negative 1.33. But I just barely found this area right here to be 82.3%. But which area in this picture am I looking for?
The parts not shaded in?
Yeah, actually both parts not shaded in, right?
Yeah.
So that's the difference when I do this with my alternative hypothesis. I'm not giving myself the top tail or the bottom tail. I'm forcing myself to have to use both. So it's actually harder to get a significant result when you do both tails like this. You're basically doubling what you would have, the area you would have had if it was a single tail test. So if, without data snooping, without looking at the results before you start the test, if there's anything in the problem to suggest if it's one way or the other, then it's better for statistics to just do a one-tailed test. But if there's nothing, if they're just saying, I just want to see if it's the same as it's always been, it's not leaning one direction or the other, so you have to do a two-tailed test. So my final p-value, the actual probability that this could happen, which is going to be our 5th step, is just going to be 100 minus 82.3, but I am not going to divide like we do so much of the time. So P for this example is going to be 17.7%. And the question is, are the data consistent with the model? So do you feel like 142 is consistent with the statement, I guess we could say, that 75% of the seeds are going to turn out blue? What does this number mean?
Is that like how far off it is?
This is, so no, not quite. I see where you're going with that. So this, the 1.33 is kind of sort of the how far off it is. It's 1.3 standard deviations away from average. Is that a long ways away from average? No. A z-score of like 2.9, we're like, whoa, that's a long ways away, right? But 1.3 is kind of like, oh, that's not too bad. That's not too far off, okay? So 17.7%, what you want to do every time you see this number is you want to ask yourself, is that less than 5%? Because we consider less than a 5% chance kind of hard to come by, right? If something has less than a 5% chance of happening, we're kind of like, ugh, I don't think I'm going to put my money on that one. And then there's a 1% chance, okay? Are you going to pay $5 to enter a drawing if you know you have less than 1% chance of winning that drawing? I wouldn't, right? I guess it depends what the prize is, or how lucky I'm feeling that day. But generally speaking, okay, 5% is one of the cutoffs and 1% is the other cutoff. So if this had been less than 5%, we would say this is significant data, which tells us that that 142 is significantly far away from the 150. But in this case, it's not less than 5%. It's actually a lot higher. So what this number is saying is that if the box really, if the seeds, I guess we could say, because we're talking about seeds, if the seeds really work like this, okay, in the bag, there are always 3 blues and 1 white, or 3 blues for every 1 white, like, right? There could be lots of seeds in there, but if this ratio exists in the bag of seeds or in the collection of seeds, how possible is it that we could grab 200 seeds and get 142 that were blue? And the chance is 17.7%, which is actually decently likely, right? If you had an 18% chance of winning, would you play? Heck of a lot more than if I had a 1% chance of winning, right? So this is what we consider not significant. It's telling us that 142 is not too far away from 150. 142 is perfectly likely if you're pulling out of this box, okay? So our ending is not significant. Significant. Okay, a lot of times we use this phrase, fail to reject the null hypothesis. For some reason in statistics, it's like the goal is to reject the null hypothesis. We're trying to run the test to see if things have changed, see if things are better, to see if someone is lying. So we're always trying to reject the null hypothesis. It's kind of a disappointment when we find that our results are just whatever, luck of the draw, okay? So this means that that 142 could have just happened by chance. Just luck of the draw. Some people might get 150 blue exactly, but this person only got 142, but that's not super unlikely. Okay, it could have just happened by chance, no big deal. So we say it's not significant. We fail to reject the null hypothesis. The true question says, are the data consistent with the model? The answer to that, so the actual answer, now that I've run out of room on my paper, the actual answer is yeah. Okay. What happened in this particular sample seems consistent with the fact that 75% are supposed to be blue. So, good?
Yes.
Cool. I know it's always a little easier when I like go through the whole thing with you, but I think if you have a couple under your belt, then maybe you can try one. Okay, do you want to do another one, or do you have like another, just like a little question and not necessarily a whole thing?
I think I'm good.
You're good? Have you guys tried anything with the 2 sample stuff, the new assignment?
No.
Okay, so you run those tests the exact same way, but imagine if you have 2 samples, like what's your expected value going to be? if there's two different samples going on. So it's kind of like this. Let me just show you really quick so you have an outline to give you a shove in the right direction. So if you have two separate boxes, okay, and these have to be, so be careful, they have to be two samples. It cannot be information about a population and then a sample.
Wait, so is this one like
I didn't hear what you said. Sorry, you said, is this one like, what? Kaya?
sorry, what?
So you said, is this one like, but I didn't hear the rest.
Oh, I'm so sorry. So like you said, like the two samples, was that because like number 8 we had to do two samples? Was it like something like that? Is that you're talking about?
No, we don't get, so number 8, they're just gonna have you compare the market survey from the bookstore. Are you talking about page 497? Yeah, okay. So on this one, you're actually not gonna consider it a 2 sample test because, let me show you, it says national data show that it's 13 years with an SD of 3. So that is not technically considered a sample. Yeah, so that's when like they're actually taking, let's say it was the ACT. If we got numbers from the ACT and it said the national average on the ACT is an 18, we don't consider that a sample. That is actually a whole population.
Okay.
So this one, number 8, you're going to run just like the one we just did or the ones that we've kind of been doing. The box is going to be that information about the quote unquote nationwide average, and your draws are going to be that market survey that they talk about. Once you get to the latest assignment, so the latest assignment that starts in chapter 27, it starts on page 503. So this is the page 503 and on stuff. Then you're actually getting into 2 samples. So let's say like you are trying to decide if girls like chocolate ice cream or vanilla ice cream compared to boys. Like who likes chocolate the most? Is it boys or is it girls? Okay, so let's say you take a sample and this is all boys. Okay, so you take a sample of boys and then you take a sample of girls and you find, and your actual sample numbers, you would have like, let's say, I don't know, let's say 30% of boys like chocolate ice cream and 45% of girls like chocolate ice cream, okay? Because they're both obviously samples, and it would have to tell you in the problem, like this particular sample had 75 boys and maybe we only found 60 girls to complete our survey or something like that. It actually doesn't matter if they're not the same size. They just both have to be samples, okay? So you just have to watch out super, super close for that, because occasionally you'll see, like you'll jump into a question and as soon as you see that there's 2 averages and 2 SDs, you think, oh, it's a 2 sample test, so I'm gonna run it as a 2 sample test. But maybe it's not, because maybe the first set of numbers is either in the past, which isn't considered a 2 sample test, or it's like data about the whole population. Okay, so watch carefully for those, but I just want to show you guys this really quick. From this box, we would have its own expected value. We expect, maybe we didn't really know, so we were just expecting half of boys to like chocolate and half of boys to like vanilla. And then same for the girls. We're expecting half of the girls to like chocolate and half of the girls to like vanilla, okay? So what we're going to do on a 2 sample test is the expected value of the difference. So instead of having these 2 separate expected values, we just have one expected value and it's just you just subtract the two. So it's just 50% minus 50% equals 0. Does it make sense to you that we expect the difference in the percentage of boys and girls that like chocolate ice cream to be 0? Because we expect, like, our null hypothesis is that boys and girls are the same. They don't have different opinions. So the same percentage of boys and the same percentage of girls would both like chocolate ice cream. Okay, so that would serve as our null hypothesis and our expected value of our difference. The only thing that's going to really change calculation-wise for you guys is this. SE difference just has one extra step to it. So if I'm trying to find the standard error of the difference, then I have to know the standard error for the boys, and I have to know the standard error for the girls, and then we're gonna go like this. We're gonna take the standard error, I'll just do a little b for boys, and I square it, and the standard error for the girls, and square it. Okay, and because I square root it, it kind of gets rid of that squaring. It's kind of like the same thing we do with standard deviation. We don't exactly just find how far they are and then find the average distance away, right? It's that same kind of mentality. It's like that RMS, root mean square. Okay, so you would just treat these, your standard error and everything, exactly the same. It's kind of like doing two problems in one problem. And then you just combine the two expected values to find the expected value of the difference. And then combine the two standard errors to find the standard error of the difference. And then you get to just follow the normal curve, just like we always do. Kind of, sort of. Is that Katie? Did you have a question, Katie?
Yeah, it like cut off is right in the middle of it.
Oh, sorry.
You're okay.
Okay, so I was just talking, so did you get this part, the whole 0 thing?
Yeah.
Okay, so this is just 0 because we're expecting boys and girls to be the same. Then we would have a separate standard error for boys and girls, and then we put them together like this. So you just take the two separate standard errors and square them, and then you add them together and then take a square root. This will be the actual SE that determines how big these spaces are right here. So this will be your expected value in the center, as always. And then that gap will be the SE of the difference, not the two separate SEs. And it kind of, if you read the beginning of chapter 27, it kind of goes through kind of a light version of why that math exists, why it's not. Can you guys still hear me?
Yeah.
Okay. Because, like, let's say the standard error of the boys was like 5 and the standard error for girls was 4, just based on the numbers, maybe the different sample sizes, whatever it is. If they have two different standard errors, it talks in the book about why you don't just add both errors together. And basically the reason is because in your sample, you might get, in that particular sample, you might have a few boys on the high end, but it might be, so like their error is positive, but some of that might be canceled out if the girls in your group are on the low end, so their standard error was, or their chance error, I guess, was negative. So it might cancel each other out. It won't always like combine both errors and make it a really big error. Sometimes it's that, like, kind of like when you take an average, you know how if you have like two really extreme values, but one of them's positive and one of them's negative, they kind of cancel each other out. So that's kind of the idea behind this SE difference. You don't just have to take the two standard errors and combine them and have a really big error. It's just kind of sort of like it's not an average of the two errors, but it's only just a little bit bigger than the first error, not huge. So in this case, if we had 5 and 4, we'd have the square root of 25 and 16. So our standard error for the difference would have been 6.4. So do you see how it's a little bigger than the standard error of just the boys, a little bigger than that, give or take, but it's not 9. It's not all of the errors combined. So this is honestly like figuring out that the expected value of the difference is just subtracting them and then using this formula for the SE difference. Everything else is basically going to stay the same when you do the chapter 27 work. So, okay, what else do you want help with? Anybody?
I'm good.
You're good?
Me too.
Okay, all right, so real quick, the plan, we just have this 2 sample steps, so give that assignment a go, like maybe read through the beginning of chapter 27, just kind of like see how it all works together. Give that assignment a go. And then there's only one other concept I need to teach you, and it's just when you have like multiple like categories. Like let's say the sample or the fun thing we would have done if we were cool and still in school is their M&M used to, the company, Mars company, used to advertise what color of M&Ms they put in their packages, because some colors of M&Ms are more quote unquote aesthetically pleasing and therefore they seem tastier to you. Anyway, it's weird, but they don't advertise it anymore because too many people were getting upset that their bags of M&Ms weren't matching what M&M was advertising. Crazy, right? Who counts? Who cares? Anyway, so there's like this data out there about what the distribution of the colors is supposed to be in one of those little bags of M&Ms. So what we were going to do is everybody would have their own bag of M&Ms, and you count up how many browns, how many yellows, how many oranges, greens, blues, reds you have, and we compare that. But because there's so many different categories, you can't compare it. Like you would have to run a separate test for the blues and then run a test for all of the yellows, your yellows compared to what they're advertising yellow should be. Run a test for orange, run a test. Does that make sense? Like that would just be ridiculous. But there's this fancy test called a chi-squared test. And you're able to put all the data together. And it's actually a pretty like straightforward little formula. It's just some people get caught up in like wait, where does each number go? So I'll make a video for that. That'll be our other new concept. And then I'll probably post, hopefully, I don't know, depends. Maybe Friday, I'll post about what UVU already sent me the test. So I'm going to peek at it and send you guys some information about what kind of questions are going to be on that 4th exam. It's just so we're ready for it. So anyway, any other questions or concerns?
Nope.
You're so good. Okay. All right. Well, thanks for joining me. I'll talk to you guys later.
Thank you.
Thank you.
Bye.